Okay, so let's go for the industrial part of the CLEARSY Safety Platform. So a quick agenda of this section. We will start by presenting what are the required components and what kind of typical development cycle you have to follow if you want to end up with a safety critical system which is certified. We'll refine the level crossing example in order to define what is vital and non-vital in terms of interfaces and how to implement it within the scope of this conference. Then we will dive inside the implementation for both hardware and software. And finally, we will see a real implementation with a physical mock-up with a 3D printed barriers and some motors. So the required components for making something industrial is to first start by using the CS0, which is a vital computing board, which has been certified in January 2021. So it's the board on top left of the slide. This computing node has to be included inside the motherboard. So for the sake of reuse existing works, in this example, we'll use the starter kit, which is provided by CLEARSY and offers 32 non-safety critical inputs and non-safety critical outputs, and which also offers a USB interface, which is convenient for the purpose of a demonstration. For programming the board, you will need ICD4 or ICD4, which is programming tools from microchip. A programmation cable, obviously, for connecting the programming tool to the computer board, and a few wires, so USB, DuPont wires, and obviously a laptop for development. Just to remind where we are in the overall flow of the presentation. So for the industrial version, you have more degree of freedom. You can modify the scheduling of the main loop. You can define when you want to call the sanity checks, so the built-in self-test. The F transfer function can be designed in sequential or in interrupted code with B or C. For vital and safety parts, you will need to use the B language. And you have also full freedom in terms of design of the data acquisition and output controls. So basically, it's more adaptable to your own specific needs, but it also requires more works. Everything is implemented, so it's safety ready, and you have to design a motherboard in which the computing board will be plugged. The development cycle of a safety critical system relies on standards, and standards implies to have a very well-defined design cycle to ensure a high level of quality and reduce the risk of errors and bugs. So the first steps consist in splitting the feature between vital, so safety critical, and non-vital features. Then you have to follow the prescription of the standard, obviously, and if you use the CLEARSY Safety Platform, then you will have to comply with what it's called the Safety-Related Application Condition, so SRACs, which is basically the exported constraint of the platform. So if you meet all the exported constraints, then you can rely on the fact that the platform is safe. The design steps for using the CLEARSY Safety Platform consist in designing your custom hardware interface. So here, it's basically the main motherboard plus an extra board that we will discuss just after. Implement your own business logic. So in our case, the level crossing logic. And finally, perform the safety demonstration and assessment to reach certification level. So a few words about the safety-related application conditions of the CLEARSY Safety Platform. So it's a list of 24 exported constraints, which are addressing various fields of the topic. 5 of them are related to the system design, 11 to software, 3 to hardware, and 5 to exploitation and maintenance operation. For this talk, we will focus only on 3 of them, which will be detailed just after in the next slides. And if you want to have a look at the full list of exported constraints of the CLEARSY Safety Platform, you can find them on GitHub. So the idea here is not to read all the text. I will give you some fast way to understand what is below. So the first one is related to restrictive value. So track 1 is called restrictive value. And the idea is before designing a safety critical system, you have to define a restrictive state in which your safety property, the one you want to ensure, is obtained. So in our case, basically, as Thierry said before, we want the barrier to be closed when there is a problem or when there is a train. So we define the restrictive state as barrier being closed, and we need to be sure that when there is a failure or when the platform is unpowered, then this property of barrier closed is held. The track 3 is called B0 proof. It's related to the fact that the software executed will be executed correctly, but you have to execute the right software. So execute the right F, but execute F right. So in our case, what we recommend is to use the BFormal method, which ensures that the implementation is bug-free related to its specification. Other means exist, but the best way from our point of view is to use the BFormal method for performing this, to ensure that you are executing the right F. And the last one for this presentation, it's called composite safety. So it's the track number 4, and it's not illustrated directly in the education version. It is the fact that we have 2 independent chains, so 2 microcontrollers that are cross-checking all the time. And you cannot take a permissive actions with only one of the 2 microcontrollers, because in case of failure of the other microcontroller, you cannot enforce that you will reach the safe state. So it's something to have in mind since the beginning of the design of your solution. Something permissive has to be performed by both microcontrollers. So in our case, one microcontroller shall not be capable of levering the barrier up on its own. When you meet all the safety properties, the safety-related application conditions of the CLEARSY Safety Platform, you will benefit directly from the certificate, and you don't have to handle a lot of things. So you have some guarantees that are offered by the platform. They are listed here. So you have a guarantee against clock drift. So you have a time counter that you can trust with a 105 ppm accuracy. You are guaranteed that the software that is executed is identical to the one you have loaded before. You are protected against memory corruption. You are protected against RAM corruption or damage on the arithmetic and logical unit. So when you perform 2 + 2, you always get 4, or the platform is in shutdown mode. And you also are protected against error on the configuration of the peripherals and internal register of the microcontroller. If you don't use the CLEARSY Safety Platform or you don't meet the application conditions, then you cannot have this directly. This guarantee are not offered, and you have to demonstrate that you address all this topic by a dedicated means that you have developed on your own, which is, trust me, quite time-consuming. Let's dive more deeper in the level crossing example. So here we'll just discuss what it's safety critical and what it's not. So we have 4 interfaces, 2 inputs, one for the announcement pedal and one for the freeing pedal, and 2 outputs, one for the barrier and one for the signal. The first thing that we can notice is that being safe for a given interface is not always the same and depends on the context. For example, the announcement pedal, what we are fearing is to miss a rising edge, so to not count an axle that it's entering in the dangerous area where there is a road. But for the freeing pedal, the feared event is the opposite. In fact, it's to count wrongly an axle that it's exiting the area. Another property that we want to ensure for the announcement pedal is to acquire its value frequently enough, because if we have delay in the sampling of these inputs, we can fear that the train reaches the road before we take any restrictive actions for, like, closing the barrier. For the barrier and the red signal, the idea is to ensure that when we want to close the barrier is closed, basically. And when we want to light up the signal is on. Unfortunately, within the scope of this conference, we cannot cover all these interfaces with the proper integrity level. So we made choice. From an hardware point of view, everything will be done with the motherboard. So it's non-vital hardware. So in order to have one vital interface, we add an extra board, which is a safety critical circuitry for driving one output, and it will be used for the barrier. So the barrier will be controlled through a real industrial hardware that can ensure a SIL4 level, so the highest integrity level. And in terms of software, the management of the barrier will be done through a full vital implementation. And for the input, we will only focus on the guarantee of timings. As the underlying hardware is non-vital, it does not really make sense to develop safety critical software for non-safety critical hardware input circuitry. Before moving inside the implementation, just one slide about the properties that we want to guarantee. So the property that we want to guarantee is that the barrier is open only if the system has seen during the last second the area not occupied. So in any other case, if during the last timing slice from between no and no minus 1 second, if there is one axle or more in the area, then the barrier shall be closed. Here, the 1 second value is simply a placeholder. It's a software constant, and it corresponds as a first approximation to the time of travel of the fastest train between the announcement pedal and the road. So it's the time, the maximum delay that we can have before closing the barrier. We had an extra constraint which comes from software analysis, which is related that if a variable overflow, we can loop to 0 and consider wrongly that the area is free, and then the barrier will be wrongly commanded in an open state. So we limit the number of axles within the area, so between the announcement pedal and the freeing pedal, to 8. So in terms of implementation, the hardware setup looks like on the drawing. So we have the computing board, so CS0, plugged into the motherboard, which provide inputs and outputs for the signal. The output for the barrier is controlled through a dedicated board, which is called safety critical output hardware. What it's worth noticing here is that we have 2 paths for the acquisition of the push button of the announcement pedal and the freeing pedal. Each path is connected to CPU 1 or CPU 2. The idea is to meet the requirements of composite safety, because if you have your inputs connected to one microcontroller and this microcontroller forwards the information to the other one, then you break the composite safety constraint, because the first microcontroller, which is in charge of forwarding the information, can forge the corrupted data to the other microcontroller, and by this means take the full control of the system. In terms of safety outputs, we use 2 relays in serials. The use of 2 relays is also motivated by the composite safety, so each relay is controlled by 1 microcontroller. And if you zoom out from the board, you can see the safety critical output dedicated board as a converter from 2 frequency into 1 on-off outputs. So 2 frequency, because frequency 1 is generated by the first microcontroller and frequency 2 is generated by the second microcontroller. And we use a frequency because if the platform is frozen and keep the current state, then it's no longer a frequency and the output will be restrictive and the barrier will close. So a quick overview of how it looks like on desk in lab. So here you have the full setup. So that's the CLEARSY computing board. So it's only computing a node with the 2 microcontrollers. Here you have the motherboard, which provide inputs, computer interface, outputs, and a way of plugging the computing board. Here you have the programming tool from microchip, the programming cable, which on one side is plugged on the programming tool and on the other side will be put directly on the vital safety computer. 1 USB cable, okay. And the software design laptop. Here you have the safety critical output board, so the one dedicated with the 2 relays that are in white. So the white boxes are the relays, and you have 2 independent channels. In the middle, you have a lot of wires. And here you have a plywood plus the barriers, the 3D printed barriers, and the 2 buttons for entering and exiting the area. In terms of software, the CLEARSY Safety Platform software is bundled inside a single tar file, which contains documentation, ready to compile examples, and the official CLEARSY Safety Platform library, which is a precompiled binary library, which provides all the primitives for the safety built-in self-tests and other software primitives and functions for performing your work. In terms of design, what it's remaining is to design non-vital source code, so which will be located in the nr_src folder, nr for non-replicated and src for source. Here you will find basically the driver interfaces for your custom interface and all the scheduling of the application. The safety critical software will be written in bformal method and will be located in the r_src folder. And you will find the model for counting the number of wheels in the section, how to generate the frequency for the safety critical outputs hardware, and the deadline mechanism for ensuring that the inputs are pulled at the correct pace. And finally, you have a single command tool for the generation of the binary. Here you have a screenshot of the file tree structure of a typical project with the CLEARSY Safety Platform. So you have NR and SRC for the C source code, RSRC for the replicated source code. DCC builds folder is generated by the compilation toolchain, and it contains all the intermediate files and the final binaries. Framework library is meant for holding the precompiled certified binary. And you have 2 extra folders, which are toolchain config and toolchain resources, which are for configuring the atelier bay and fine-tuning of the project that will not be covered today. And in addition, at the root level, you have a config file, which provides the name and the list of all the files that are required for the compilation. We will now dive more deeper in the software architecture, first in terms of scheduling and C source code, and then in terms of B model. So at a top level view, the software is scheduled by an infinite loop, which perform input acquisition, execution of the B model, so safety critical software. Then we apply the output for the signal, which is non-vital in our case, and we call all the built-in self-tests. In parallel, we have some asynchronous events managed by interrupts, mainly for communication between the two processors, communication with I/O interfaces through I2C, and an interrupt calling, which is in charge of calling B model for the generation of the frequency. So the component view, in yellow, you have the safety critical software, which is developed in B. And in gray, you have the non-vital software. So in the middle, you have the project-specific part. So we can see that on the middle left, you have the main.c that it's calling the built-in self-tests and calling your own custom logic error_f LC treatment, level crossing treatment. And in the right of the middle box, you have the interrupt, also implemented in main.c, which is calling another part of your B model. On the left of the picture, you have all the drivers layers in charge of the interface with the real world. So all these parts are hidden in the education version, but are available for the industrial version. And in top, you have the CLEARSY Safety Platform library, which provides some API entry points and also all the built-in self-test primitives. A few metrics about the software. So we compare here what has been developed specifically for the level crossing in comparison to what have been performed for the CLEARSY Safety Platform library. So in a nutshell, we can see that in terms of safety critical software, level crossing only represent 8% of the work. And in terms of non-vital source code and drivers, we are the repartition, the split is 20% for the example and 80% for the application, for the laboratory. So it's worth using the CLEARSY Safety Platform. It will save you a lot of time. In terms of structure, if we look at the main.c, so the main loop, the infinite loop, on the left, you have the scheduling of the steps of the execution. So we first acquire the inputs, then we perform a debouncing algorithm. Once our inputs are stable, we provide them to the safety critical software, the one in charge of managing the level crossing. We have some auxiliary function just to show that we can do other things inside the platform than just the main application. And finally, we call built-in self-tests, so BIST, which are all the integrity tests to ensure that the platform is healthy. And finally, we control the level crossing lamp in a non-vital way in our example. So for getting the inputs, what we can see is that you can you can write regular C and you can get some primitives from the platform. In our case, nrf get time ms and nr_f get time, nr for non-replicated function. And these functions are provided by the CLEARSY Safety Platform library and provide the system times since the startup of the system. The second part is the debouncing algorithm, so there is no need to dive in how we debounce a push button. It's not really interesting, but just to see that we can perform arbitrary logic and algorithm directly written in C. Then we have to call the core part of our application, which is rf_lc treatment. That it's written, it's an operation of the B model. So the software is replicated, and here we see that due to this replication, we have to call replica1, so r1__lc treatment, and then r2__lc treatment. But here, the two functions are generated, and when you write your B model, you only have one operation to write. Then we have the built-in self-test. So here we made the choice to write them in sequence and to call them in sequence. Once again, the scheduling strategy is free to the end user. So if you have an application where your timing is constrained at some time and not in the other time, you can decide to perform part of or all of these tests at a different moment. And finally, we have the management of the level crossing signal. So what is interesting here is that we can retrieve from the C source code information from the B model. So non-vital software can read some values from the safety critical software, and it's performed with getter function. And here we need to call only one because the guarantee that the two replica have the same value is ensured anyway. At this stage, we have the management of the inputs, the management of the signal, and the remaining part is the barrier itself. So as said before, we need to generate a frequency to control the barrier. So the frequency is generated with a timer interrupt inside the microcontroller. So the timer is always running and the interrupt service routing is always executing since the beginning. And it will apply a square wave or not, depending on the state of the B model. And the value inside the safety critical software is voted using the safety end primitive of the library. And we have two getters functions, one getter function replicated, which is called get set address and value, which return a pair of an address and the value to apply at this address. And the address is the address of the register of the corresponding pins of the microcontroller. And the value is the value we want to apply on this pin. So this way, we can vote between the two replica before applying an output in the physical world. Now we can discuss more in details the formal model, so the one in charge of the safety critical software. So we start with the assertion that define our safety property, which is that the zone is free only if during the last slice of time between now and now minus 1 second, no axles have been detected inside the area. And then we have other conditions to say that the barrier is closed when the zone is not free. The model of the counting of the axle is presented here. So we have LC treatment that we have seen before. It takes as input 4 parameters: the clocks, the state of the announcement pedal, and the state of the output pedal. We ensure through formal methods that the parameters have the correct types. Then we perform a filtering to detect only transition on the pedal. And if everything is fine, then we increment the number of axles inside the area. And we update the watchdog timeout if everything is fine. And finally, we apply the state, so it's the getter we see in the interrupt service routing of the timer. So it's simply a getter which returns the address and the mask of the register of the pins and the value we want to apply on the pin. And what is interesting to notice here is that we will return an on state on the pin only if the zone is free, so it's what we expect, but also if inhibition is false. So what is inhibition? Inhibition is a variable managed by the CLEARSY Safety Platform, which will be true as long as it will become false when all the tests have been passed at least once. So if one of the self-tests has not been passed, then the inhibition is set. It's to manage the startup time of the platform when all the tests have not been performed. When you have written all your source code, then you have to define a project, and it's done through the configuration file. So it's a file, it's a text file in makefile format, which simply contains a list of predefined constants that you only have to happen with the proper values, which corresponds to the files that you are using inside your project. So you can modify compilation options, define where is the manifest of your B project, and so on. And once you have done everything, sorry, one slide about a short summary of what we have just seen. So the source code is organized in two parts. One is safety critical and written in B, and one is non-safety critical and it's written in C. You have no limitation in terms of algorithm complexity for both the B part and the C part. You can add driver for your custom hardware. So here we have added some source code for managing the vital output board, so the one which is sensitive to the frequency. We have seen that the C source code can trigger B model operation. The operations that can be seen from the C source code are simply prefixed by R_F. You are free from scheduling the program the way you want. We have also seen that the C source code can get data from the B model from getters. And finally, the B model can retrieve parameters or variables from the non-safety critical part, either by operation parameter, it's what we have done in LC treatment, or by naming convention. If you call a variable nr_v for non-replicated variable, then it will be visible within your B model. It's not illustrated here, but it's in the documentation. And final point, you can use interrupts for both safety critical part and also non-safety critical parts. So when you have written all your source code and you have written also the configuration file, then you can compile and load your application. So for compiling and loading, here you have the structure of the project with in the framework library folder, you have the tar file. In NRSRC, you have all the C and H files. RSRC, you have your models, refinement, and implementation. You have an extra script, which is used for compilation. So you call the script with the -C options for compiling, your username plus the target, so in our case, release. It's compiling, takes some time. And once the compilation is done, the results will be provided in a DCC builds folder, which will be automatically appended to your working directory. So you have intermediate file and MCU1 and MCU2, which are the two binaries that you have to load on the target. So when you want to load on the hardware target, you connect the programmer, you power up the board, and you click on program. Programming is performing. And once it's done, you disconnect the first microcontroller, you select the other binary, you connect the second microcontroller to the board, and then you click on program. And once it's done, you only have to recycle the power of the board, and then you are ready to play with your new software. So, second video, how it looks like when it's loaded. Too many videos to find. Okay. So here you have the setup. So at startup, the barrier is closed because we haven't performed all those built-in self-tests. When inhibition is removed, the barrier opens. We count 4 axles entering from left to right. The barrier is closed and the signal is on. We made the 4 axles leaving the area and the barrier opens. We had 1 axle, the barrier closed, 1 axle, the barrier open. And in reverse order, we have 4 axles entering from left to right, from right to left, sorry, and 4 axles leaving the area. So that's for the nominal case. We will now see what happened in case of dysfunctional use case. So we will discuss all the example and scenario before, and we will have at the end a video for summarizing each of these cases. So the first one is related to not calling the built-in self-test frequently enough. What happened in case of an overload of the CPU resulting in a slowdown of the execution? What is the results of the corruption of the flash memory, a corruption of the RAM, and the case of the systematic design failure? So if we do not call the built-in self-test frequently enough, the system will simply shut down because we don't know if our platform is healthy or not. So we decide to take the safe state, which is barrier close. So in order to simulate this behavior, we replace the regular function in charge of calling all the built-in self-tests by a function that calls all the built-in self-tests normally during the first 15 seconds, sorry, and then we forgot to call one of the tests by simply commenting it. And in this case, as we will illustrate after, the barrier closed when after 15 seconds. The second dysfunctional case that we can study is the slowdown of the execution. So it can be the result of denial of service. It can be the results of an exotic branch of your application that is executed once a year, but take a lot of time before returning. So in this case, we will not acquire the states of the announcement pedal for a potential long time, and the train may reach the road before we have taken a restrictive action. So there is a real collision hazard in this scenario. So the behavior of the system in this case is to shut down because you don't meet the timing and you don't comply with the assertion that we have seen before. And in order to simulate the delay in processing, we have written this small function, which called during the first 15 seconds, 15 for the same reason as before, to have enough time to go after the inhibition period of the startup. So during the first 15 seconds, we execute the software normally, and then we delay the execution, the call to the LC treatment function. And as it will be demonstrated just after the barrier close. The case of the corruption of the flash. So during the life of your product, the memory can be corrupted. If it's a picture on your smartphone, it's not really critical. If it's the software of the level crossing, it can have a larger impact. So in order to simulate this behavior, we directly edit the binary file manually, and we flash the modified binary directly on the target. And we will see that in this scenario, inhibition will never be removed, and the board will start by complaining about a corrupted flash memory. Corruption of the RAM, so it can be due to a cosmic ray or an EMC perturbation. It can be also the case if you have one of the two compiling toolchains that perform an error, and one of the two replica has a corrupted value. The associated risk is if you write the variable in charge of saving the state of the area, if it's occupied or not. If you modify it in the way that the area is free, and it's not the case, then you will have a barrier up, which is not allowed. So in order to simulate this behavior, we have added some information to the source code. So these information are reverse engineered, so they are not accessible regularly from the C source code. So it's basically the organization of the safety critical variables and their addresses, and we write a random value, so here 0xCA inside the memory. And in this case, the corruption will be detected, and the system will shut down and barrier will be down. And the final dysfunctional case that we will illustrate today is a case of a design failure. So as explained at before in the properties that we want to guarantee, we want to detect if there is more than 8 axles entering in the area. So 8 here is for the convenience of using the mockup, because max uint 8 it's 256, and it's quite long to press 256 times on the button. So we have limited to 8, but if we have an overflow, what we can fear is that due to operation condition, let's say every train has 6 axles, you do some maintenance operation on the announcement pedal, and you count 3 axles during night. You remove your maintenance operation, and the first train that it's entering the station the day after has 6 axles, everything is fine. 6 plus 3, it's equal to 9. Yes, in mathematics it's correct. If the variable overflow after 8, it's equal to 0. And in this case, you will have a train in the area and a counter of axles that it's equal to 0, and a barrier that it's up. So there is a real collision hazard, and in this case, if you don't prove your model, and if you don't analyze this kind of failure mode, and you have a systematic design failure, you are executing you are right executing the wrong F, and in this case, you will kill people. So a video for illustrating all the dysfunctional cases that we see before. So they are in sequence. So the first one is the built-in self-test. So we do not call the built-in self-test frequently enough. The barrier is open, and then after 15 seconds, it fails. So you have a message saying that you have not reached the deadline. The second one was the slowing down of the execution. So same, it looks very similar, but in fact the result is always the same. So the corruption of the memory, you have flash memory corrupted printed all the time inside the debug interface, and the barrier will not go up. What you can notice here, it's also the case for the other video and use cases, is that the signal is dark. It's because it's managed in a non-vital way, and here we shut down the platform, so we cannot provide energy to outside. So due to gravity, the barrier closed, but the signal cannot be on. And for the systematic design failure, we will press 9 times the entering button, so the announcement pedal. And here you have an error, and you can see that even if we press 9 times the button for freeing the area, the barrier remains closed. So in case of failure, you have, in case of shutdown, the red LED lights up.
We have a question before moving to the next part, the last one from Jaya Prakash. Is this level crossing model installed by CLEARSY anywhere physically, or is it only a prototype?
Yeah, so it's only a prototype. There are various strategy, and it depends of country and customers the way level crossing are implemented. So it's only an example here to be representative and to have some materials to discuss about. ID used inside the level crossing have been used in other projects and applications, but a level crossing itself, it's not developed, and it's not this model specifically for a level crossing.
Okay, so time for the conclusion. So as a summary, so the CLEARSY Safety Platform for what for? So 3 different versions. One is available since 2 years ago. One is available for free for software simulation, and the one for industry is going to be available this summer. And you can see that the first 2 are, well, have already been used for education, for different profile, for theoretical profile, for the introduction to formal method, but as well for people with a more practical profile on embedded systems, IoT. If you want to go for demonstration and proof of concept, of course, the boards, both boards are could be used. And if you want to go for complete project, of course, because the education version is not fit for safety critical applications, the best is to go for the industry version. Just to sum up what was being said the last hour. So what we've learned, we well, hope you learn a lot, maybe some different things depending on who attending the tutorial. The safety, so you can see that safety, you have a lot of things coming with the safety, the reasoning, things about the implementation. When you think that you're developing software, it compiles and it works, it's very far from the reality. You have seen that you can use formal modeling for the software. You can prove it, even if the example here is not trivial, but it's not very complicated. We have sensors, we have a counter, we increase, decrease the counter, but we already have subject of that you need to pay attention to in order to avoid mistakes. I hope now that you have a better understanding why safety industry is more looking for engineers with a big E than just for software developers. It's no offense, because for safety applications, you understand that you need to handle more aspects of reality than just software. And for my methods, when they're used for safety, are only I would not say small part, but just a part of the story. So if you have any further question, just ask me. You know my address. You have a lot of resources available. For the GitHub, you have the tutorial, you have the coding handbook, there is a YouTube channel, there are web pages, you have papers as well. And thank you for your attention, and remember, formal is fun.